Okay, I believe everything is in order. Yeah, we're just going to continue on with the 2021 Exam 1. Now, technically speaking, we left off at Part B of this question, but rather than have to sort of re-educate ourselves on that, it's probably better off just leave it and move on to the next one, question 7. Okay, let me chuck in both Exam 1 and the solutions. We're currently up to 7A. Let me chuck that back in so Estelle could also see the documents. We're up to 7A right now. And one more time. Cool. If anyone's still lacking the document, let me know. I'll chuck it in. Show that K equals 2. These questions are always solved the same way. We're told we have a random variable that's described by a piecewise function. Proving that K equals 2 is solved the same way every time. One of the key things to understand here is that this is continuous probability. It's continuous because you've got a probability function described by f of x, some sort of piecewise. So we've got to think about some of the main key features of continuous probability. One of the things that's true of all continuous probability is going to help us with solving this particular question. Anyone got any ideas so far?
For A.
Yeah, for part A.
It's just you do, because it's probability density function, you do an integral from 1 to 2, because that's where the function part actually applies. And then it equals 1.
Yeah, correct. That's precisely it. Make the function equal 1, or at least rather the integral of the function equal to 1. That's what this is all about here. Integral, you do your anti-diff, capital F of top minus capital F of bottom, simplify, 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 you'll get all the way there. Nice. Part B, E of x. It's also a fairly stock standard question. I believe it shows up in the formula sheet as well. Yeah, x times x, correct. You're going to do the integral of x f of x. So you're literally just going to stick an x at the front of there and more or less repeat what you just did, except you're not going to set the integral equal to 1. You actually want to know what that integral will then equal. It'll be good for you guys to actually do the arithmetic on it for that one in particular. Practice a bit of integral math. Let me know when you get an answer.
Is it log E of 4?
Yeah, natural log of 4. That's it. Nice. As far as the working out, or at least roughly speaking, what the working out could look like, when you do your x f of x, that's going to cancel into just being a hyperbola. So the antidiff of that, logarithm. Nice. Fairly easy self-contained one there. That should be 3 free marks there, more or less. These are also fairly free, at least as you get more and more confident with things. Question 8. Find the rule of the function. So some of the key information we're given here is the derivative of the function and the location of a stationary point on that function. That is sufficient information to then find the rule of the function. That being like the original, right? You got original function, you got derivative. So you got to figure out how do we get from derivative to original.
Chris, do we just anti-diff the derivative?
Yeah, antidiff would be a really good start. It won't be the entire solution. It'll be pretty much all of it though. Yeah, antidiffing that will get you back to y equals something.
And will this be like removing the plus C?
Yeah, you're gonna have to do something to not necessarily remove it, but solve for
Oh,
what it
wait,
is.
sorry.
But
Sub in the stationary point to figure out plus.
correct. Yeah, the fact that it's a stationary point doesn't actually matter. It's more the fact that it's a point that exists on the function. At least for now, it doesn't matter that it's a stationary point. It's just some way for us to remove the x and y so we can then solve for c. Nice. This antidiff might be somewhat complicated. I would say for this one, I would actually probably to this day, I still probably look at the formula sheet version to antidiff that easier than otherwise. Roots can be a bit challenging. Diff, it's not so bad. For whatever reason, diff just tends to be easier than antidiff. At least in my experience. if you have trouble with the antidiff on that root term, can be best to look at the table of integrals for that one. The arithmetic on this one can be a bit tricky, at least in my work solutions that I wrote a while ago. I broke it down into a lot of individual steps. Probably didn't need to be broken down that much, but maybe it did. Not too sure. So if you are getting quite tricky arithmetic, it's probably to be expected.
Chris,
Mhm.
I've got C equal to 1 on 2 minus 18 root 2. But
Something went a bit wrong then.
something went wrong.
Yeah, you want to get c equals 4 as a final answer. So there's maybe, I guess, double check where you're doing root arithmetic. See if there's a cancellation that was otherwise missed. You also might want to double check your basic antidiff though. It could be another thing that might have gone wrong. It could be all your arithmetic is fine, but the antidiff might have gone a bit weird. Yeah, I was saying the arithmetic is hard, and then I realized my answer is actually slightly wrong. Um, Not c equals 4, but c equals -4 is what you want.
Yeah, I was about to say c is equal to -4 as
Yeah.
well.
Yeah, okay.
Yeah, so
Good.
it's the rule of the function, like it's gonna be a mouthful.
Yeah.
2
I can.
times x plus 6
Yeah.
to the power of 3 on 2.
Yeah.
That's all over 3.
Yeah.
Minus the fraction of x squared over 4.
Yeah.
Then minus 3x on 2 minus 4.
Yeah. And -4 is what it should be at the end. Yeah. Mine, unfortunately, is a +4. The error is right here, where I kind of just swapped the c and the 29 on 4, but I didn't chuck a negative on this c, and so that's why it ends up being positive instead of negative on my solutions. I'll fix that, but the rest of this up until that point should be more or less fairly solid for the arithmetic there. The only probably thing I would point out is how to handle the power of 3 over 2. My typical way of going about that is to split it up as such. So essentially you have 3 over 2 is just 3 separate halves. You can split that into 2 over 2, which is just power 1. So there's your 9 with power 1. And then you've got a remaining half there. That's probably the easiest way to split those up. I don't know, do you do anything different when you were handling that? Power 3 over 2?
Yeah, I basically just do the same thing as you. It's just like
Hmm.
I first do the square root of 9, and then
Yeah,
I
yeah.
do the square root of 9 to the power of 3.
Yeah, actually, that's also chill because square root 9 actually does simplify down. Right, you got 3, and then cubing that isn't the end of the world. This might be a bit more applicable when you have more like unsimplifiable roots, or at least ones that don't have an immediate integer answer. But yeah, cool. That's the rule. Lots of work there. I probably went into too much detail on this one because if you imagine trying to shove that into all the working here, not enough room really. But yeah. And then part B, nature of stationary point. We have a lot of different options there. Nature of the stationary point. So essentially what's going on there is we want to figure out, is it a maximum, is it a minimum, or is it an inflection point?
It's so what I'm doing right now, like I still haven't calculated yet.
Mhm.
Is that I'm setting the derivative equal to 1 and -1, and then seeing like what's how the function's like if it's increasing after that or decreasing.
Yeah, okay. Set derivative equal to 1 and -1. You're going to get some sort of x value out of that, out of both of those.
Like
Sure.
to
Why?
figure out if it's like a local minimum or maximum.
Yeah, okay.
I could be
Um,
wrong
and that'll
there.
spot. Um, that's probably fine because it's diff. Diff is 0 at that spot. So doing like positive and -1 either side is a pretty safe bet for gradients. Now, you might come across a weird case where the gradients are so shallow that you maybe don't hit positive or -1. Um, probably safer bet instead of setting gradients equal to a value, probably just do the two x values either side of this. If you want to do a similar approach, you would test like x equals 4, x equals 2, and see what's happening either side of that. It's a safe bet because it says it's a single stationary point, so you can never test too far either side of these points. So in fact, maybe that being the case, you probably even test x equals 0 and x equals 4, because 0 is usually an easier number to work with. You're guaranteed only one stationary point. That's the first way of going about it. Works fine. Your way might have also worked fair enough as well. It's probably a little bit more involved because you're solving for x rather than just subbing in an x value. The other method is double derivative method. It's not usually taught. I don't think it's taught in the textbook specifically, but it does actually appear literally on the VCAA report as a valid method of doing it. Yeah, we'll look at both.
Is it a maximum?
It is a maximum. Yeah. What was your method?
I did the double derivative.
Double derivative. Yeah. So that's what this would have looked like here. You do your double derivative, so derivative of the derivative, sub in the x value that you want to test. You get a negative number. Negative number means you have a local maximum. Keyword local maximum is probably the most. It's the most specific way of defining that. So if you say maximum versus local maximum, technically, you'd rather be saying local for the more accurate answer. As for the other approach, I'll have to quickly change my screen share to the exam report. I don't know how well this is going to show up, but you've got this this table approach where you've got your x equals 3, which you know is a 0 gradient, and then they've just chucked two random spots either side of that. It's a fairly safe bet to choose any two random either side because there's only one stationary point. 0 would have been probably a nicer thing to test, just because zeros are easier to work with. Yeah, any of that works fine. Is that showing up nice enough on the? Yeah, looks like it should be fair enough on the screen share. Cool. All right, let's flip that back. Yep, there we go. This was a nasty sequence of questions. When we get to B, I'll fix this up for you guys because matrix is no longer in study design. But we'll start with 9, or 9A rather.
You just sub in the point and then see if left-hand side is equal to right-hand side.
Sub in the point, left-hand side equals right-hand side. When you're trying to show that the equation is a particular thing, what you're trying to do instead is create the equation rather than subbing in points and then testing that the equation is valid. Now, real world scenario, yeah, if you want to quickly check your equation is working out well enough, then yeah, for sure. Just shove in some points that exist on the curve, and that should be fine. However, in this case, we need to actually fully create this equation essentially from scratch. That's the typical approach for a show that. You want to try and get to this answer, not use that answer to then, yeah, you don't use the thing in the show that as the working out. So now we need to figure out like, okay, this is some kind of linear equation. What kinds of things do we know about creating linear equations? a lot of flexibility with how you can go about this. In fact, you could solve literally every unknown in this triangle. The angles, all the lengths, everything like that. You don't need all of it, but you could get it if you wanted it. So, or let's just say your path may be different than what's in the answers, but there's a lot of ways you could go about it. One thing I would highlight is the fact that this is a unit circle. That should start bringing up some ideas of how the unit circle works. Anyone got any initial ideas on stuff that might be relevant? You know, whether it's unit circle stuff, whether it's how do we create the equation of the line, what kinds of things do you reckon we need to get at some point to get this equation going? Okay, let's be a bit more specific. So if we're trying to create the equation of a straight line, ignoring all the specifics of this question, what are all the ways in which you know you can create a straight line equation? What are some methods that we use to create straight lines, the linear equations?
Like use the equation,
Use the equation.
like the y minus y1
Yeah.
equals.
Yeah, that's a good one. Y take y1 equals mx take x1. That's the gradient point formula. So essentially what we're trying to get at there is if you knew a point on the line, which you do, and the gradient of the line, which we currently don't, then you could create this equation. Yeah, that's absolutely one way of going about it for sure. So that narrows your focus. It's like, okay, now my main focus is getting the gradient of this line. How are we going to do that? Another method could be, it's basically the same as gradient point formula, but you know, for gradient, when it comes to linear, that's rise over run. So if we knew the point P, the other point on this line, that could be a way to get gradient. You know, this is the sort of rabbit hole that you run down. You think, okay, I've got to create a linear. What do I know about creating linears? Gradient point or just 2 points? Cool. The other point there is P. How are we going to get P? And you just sort of follow your nose on that. If finding P is what's going to be important, one thing to note about it is that it exists both on the unit circle and on an implied triangle, right? Like you've got this hypotenuse from P to A. You've got, let's say theta's in the spot where it would be on the unit circle. You've got, well, actually it's a bit tough to work with if you do that. But point being, you've got some adjacent, some opposite side to work with there. So what kinds of things can we use from our understanding of triangles to potentially eventually get this point P going? Is anyone making decent progress on it? Or are we all stuck?
I'm stuck.
Yeah, okay. Anyone got an idea of how we could progress from here, or shall I just sort of take over? It's a tough question. It's 13% pass rate on this one. Cool. Okay. So, what did I do? Well, one of the things I thought would be important is to particularly maybe start working towards getting the point P. Now, one of the things I did, not the only way of doing it, but one of the things I've done is to start thinking about the SOHCAHTOA stuff. Right, we have this triangle here, and what we can do is we can create the cosine ratio. You got your adjacent hypotenuse. Here's your adjacent. Here's your hypotenuse. Now, hypotenuse is sorry. Here's your what am I saying? That's your hypotenuse. I think I said earlier that hypotenuse was AP. That is not good. Anyway, you've got your hypotenuse, which has the length of 2, and the adjacent, therefore, is going to be this side. And so what you're essentially doing is creating your cosine, and you've got cosine equals a half. And so for that reason, you get your pi over 3 as the angle that would be in this spot. Now, from there, we were... Okay, so I've gone on a gradient method then. The other thing we said was that potentially gradient would be another way of going about this. If I can figure out the gradient at P, the line connecting A to P, then I'll get my linear. One of the things I've noticed is when you put a right angle there, that's effectively the normal of this gradient here. And so if I were able to find the gradient of OP, then what I would be able to do is flip that to get the gradient at P that goes through, that's tangent off of P. Now, this is where the fact this is a unit circle comes into play, because now the gradient of that line, or I guess just the fact that it's a circle, didn't necessarily have to be a unit circle for this because we're just doing things in terms of gradients. Point being, tan theta gives you gradient. So this has a gradient of root 3. From there, as I said, we flip it. So you want to do the negative reciprocal, -1 divided by the original gradient, and then here's your y take y1. That's one way of going about it. You know, you could solve this entire thing, right? You could do the sine and cosine of those angles to get the x and y coordinate of P. That could be another way that you do your gradient point formula. You have 2 points instead of point and gradient. And you could use the what's it called, the Pythag theorem to get the lengths of everything here. Here's this really old thing that I drew. You got angle here, angle. You got known lengths of things. It's fairly chill. Yeah, lots of different ways you could go about that. Anything in there need clarification? I'm going to have to redraw this picture at some point. I did this in, I'm assuming, MS Paint. God knows how long ago. Any clarifications? Cool. Okay. This one, let's see. How much do I remember my matrices? The transformation that's applied here is x dash equals x, y dash equals qy, I think. Let's put that on there. X dash equals x, y dash equals qy. That's all that's saying. So we've got a transformation as such, and let the graph of the function h be the transformation of the line. So it's this equation here, the line that's passing through AP, that's being transformed by the x dash equals x, the y dash equals qy. That's the setup there. And then from there, what values of Q would force the graph of H to intersect at least once. Alright, so if you imagine Q, the fact that it's a multiplier means that it's a dilation factor. So you can imagine how it might stretch it to be steeper, in which case it never touches the unit circle, or shorter, in which case it'll cut multiple times. These are just some basics of the scenario. Anyone need me to clarify further, at least the starting point of what's going on? If not, have a stab at it. See how far you can get. This one was even harder. 6% pass rate. But we'll see how we go. This is one you don't necessarily algebraically fully solve. You kind of have to use similar methods to what you would do in a tech active, which is you just kind of imagine if I toggle Q through like a slider, what's going to happen to the graph of the line. And to be able to do that, one thing you'd probably want to do is figure out, hey, what is the equation of my new line under this transformation? That'll make it a bit easier to see when I change Q, something will happen. And maybe we'll make that as the first stretch goal. Let's see if we can get an equation for the new line before we start thinking about what's going on with it.
Sorry, I had to leave the room for a second. Can you just explain the matricey thing again?
Yeah, okay. So I've replaced the matrices with the equivalent x dash y dash on the handwritten notes in the on the phone. It basically means you've got x dash equals x and y dash equals qy. It's a transformation matrix. And what's going on there is we're transforming the y equation. It says the line through AP, which is this. We described that, well, we found that out earlier. So one of the first things before we even look at what's going on here, I'm going to start by at least getting the new equation of our line. From there, we can analyze it in a little bit more detail.
Yeah, thank you.
No worries. Has anyone got an equation for the line after the transformation? Particularly crazy. It's applying a dilation factor of Q to Y. whichever way you want to go about that, whether you do your whole x dash y dash stuff, or you just realize, hey, dilate factor of q means that we slap a q on as a multiplier of y. Either way you want to go about it, that at the bottom of the screen share is our function, our transformed function. From there, we now need to figure out, okay, values of q for which this new graph, so this transformed graph, is going to touch the unit circle at least once. So we got to figure out, okay, q is doing something to this straight line. We need to make sure it touches the unit circle at least once. So it can't go like up here, it can't go all the way down here. It's got to cut either on the, it's got to be either tangent to the unit circle, or it's got to cut all the way through it. So we've got to do some analysis. Q is a multiplier on the entire function, which means that Q is going to affect the gradient of the line, and it's also going to affect the y-intercept of the line. So if you imagine increasing Q, the more Q increases, the more the gradient will decrease, because you've got this negative number. If you multiply it by a positive, you just get a bigger negative number, a more negative gradient. And you're also going to increase where the y-intercept is. So basically, this will now cut up taller, and it will also be steeper. Not great. So, with that in mind, we already know that the last point at which this is going to touch the unit circle is essentially q equals 1. Because q equals 1 gives us the original equation that we had. Anything above that is just going to go, it's just going to go out of whack, right? We're already tangent, we can't go any further than this. If you imagine q equals 1 in this spot, you just get the original graph. So as far as like an upper bound of q, that's about as tall as it's going to get, q equals 1. We would now shift our focus into what happens as q decreases. And so as q is decreasing, you're going to get a smaller y-intercept. So you're going to start cutting through the circle, and you're also going to get a shallower gradient. Right? It's going to start getting more and more horizontal until like q equals 0. Now, reminder, q equals 0 isn't technically valid for this, so we're going to exclude it in our domain. But just for illustration purposes, if q equals 0, you would have a perfectly horizontal line, right? So it's going to cut through the two quadrant boundaries at those spots. It's going to be perfectly horizontal. Now, at a certain point, it's going to go too far. The y-intercept is going to be too small, and because the y-intercept is too small, it will no longer touch the unit circle. The question now becomes, what is that final boundary? Think in terms of symmetries here.
Is it -1?
It is -1, yeah. Was that based on just thinking, okay, if it's +1 to get this, then flipping it downwards, -1?
Yeah.
Yeah, that's basically all that was required. You can see there's no lines here for marking. It's purely an intuitive thing and being able to explore what's going on. I tried to explain this, God knows how long ago, in this. I don't know how good of an explanation that is, so maybe after class, have a read of that. If it was a shit explanation, let me know. I'll rewrite it. I wrote this maybe 2 years ago. But yeah, final answer, just making sure you're excluding that 0, because we were told all real excluding 0. That's all. Very tough question. That was the, was it 6% pass rate. It only goes downhill from here. The next one is a 4% pass rate, and the final CI is a 1% pass rate. And then II, 4% pass rate. So everyone bombed on this one, basically. And you can imagine why. There's a lot of intuition, essentially, going on. No real math required. Or no real math that you have the space for. Anyway. So in this case, we've got the graph of h that has to cut it twice. Find the values of q for which the coordinates of the intersection points, plural, have only positive values. So basically you want both the x and the y of the point of intersection to be positive. Like for example, where it is right now at point P, you got a positive x, a positive y. However, as you start shifting it further and further across, as soon as you break this y-axis boundary, you've now got a negative thing. That's bad. But if you keep going, eventually, as you breach this, you'll then go, oh no, sorry, it's just in here. Yeah, because this is in negative territory, negative y territory. So you're actually only looking from this shallow range in here. The fact that I mentioned y-axis there is kind of important. The other key thing to consider is that this is a unit circle. Alright, unit circle radius 1. That'll help you hone in on what this boundary is going to be. Maybe we'll start with that. Does anyone know what this y coordinate here is for the unit circle, right on the y-axis?
It'll be 1.
Yeah, it'll be 1. Absolutely. It's a unit circle, radius 1. The absolute max of that's going to be 1 up there. Yeah, absolutely.
Is the answer got a 2 over root 3 in it?
2 over root 3 is the fraction flipped. I don't
Okay.
quite know. Oh, well, yeah, no, I can see where you probably got that. It's, yeah, I don't know. Let's, it's like this, basically. So there's your 2 on root 3. It's just that when you then go ahead and solve for Q, it flips back over. And so, yeah, basically what you're looking for is, okay, I know the last point at which this is going to work out is for a y-intercept of 1. And so what I want to do is make sure to find Q such that I have a y-intercept of 1. So you sub in your x equals 0, your y equals 1. I don't know why I did this in 2 stages, but okay. I did y first and then x later, but okay, sure. Yeah. Q's the only thing left over. Simplify around, root 3 on 2. And then, you just use the same upper bound that you had before on there. Now, why have I excluded the boundaries?
Because if you include it, it'll intersect twice.
Well, we want it to intersect twice.
Oh, sorry, it'll intersect once.
Yeah, intersect once. Now that I'm looking at this again, I feel like that one should be inclusive. I think I stuffed that up a little bit. Let me double check the exam report. No, that's not inclusive. Why is that last one not inclusive? Because Q being that means that you're forcing the line through there. Oh, right, because 0 is not positive. Yeah, okay, that's why. Yeah, because that will be, it'll have 2 intercepts, but 0 is not a positive intercept. Yeah, okay, that's why. Fun question. It only gets harder. Maybe, I don't know. At least the marks drop. Maybe it's because, well, I imagine this one's definitely going to have marks drop because it's basically required to understand this one. So that makes sense. This one may or may not be its own unique thing. Let's see. 0 to 1 for Q. P dash is some point of intersection that is closest to A. So, you might have 2, but P dash is the one that's closest. G is the area of the triangle. Define G. Yeah, maybe this wouldn't be the end of the world. Give you a bit more guidance as well that you're trying to get it in terms of theta. Usually that's said in the spot where it says I, but just want to highlight that yes, in fact, you've got something in terms of theta, which should probably help restrict your thinking in terms of what functions could potentially be used for defining the area. There's a very easy starting point, which is just its triangle, so half base times height. A nice and easy starting point. Question then becomes how are we going to get our base and height? Again, unit circle is going to matter for this as well. This will really test some unit circle theory. Understanding exactly what it is about points along a unit circle and how we can generalize that. You're going to need the height of this triangle at some point, and the height of the triangle is definitely going to be given by the y value of p dash. You can imagine as the line is being shifted around, the height of that triangle, no matter what, it's going to be whatever the y value of p dash is. And p dash exists on the unit circle. So we've got to think of a way to make a generalized point, p dash, purely in terms of theta. You should also have a think about how do you normally get points on a unit circle? Like if I told you to find like, how am I going to phrase this? Yeah, I might just give it. X is always going to be cos theta, and Y is always going to be sine theta for unit circle stuff. The fact that theta is in the exact same spot where the unit circle would have it is a really good help here, because generically speaking, wherever you put this p dash, it's going to have the point cos theta comma sine theta, essentially. Now, obviously, on the unit circle we have specific theta values, but generically speaking, it's just cos theta comma sine theta for the coordinate xy. Probably everything. There's not much else I could explain that doesn't give it away immediately. Shall I go for it, or is someone close to getting an answer? Cool. Okay. Tough questions. Don't worry too much. They are quite low pass rates. So this is what I was saying before about whatever this point P dash is going to be some cos theta sine theta, where the y coordinate is sine, the x coordinate is cos. The x isn't really all that relevant here. What is relevant is that we're trying to do half base height. Base, well, that's just 2. We can see the full base of that triangle is going to be 2. It ends at coordinate 2, starts at the origin. And the height is going to be whatever the y coordinate is, which, as we said before, is going to be sine theta. So wherever you put this thing, your y coordinate is going to end up being sine theta. That's going to give you, you simplify that all the way down, you've just got your function g is going to be sine theta. They said find the function g. Now, when it's worth pointing out the difference between a function and a rule. We run into this same issue with inverse functions a lot, which is they'll say define the inverse function of whatever. Under those circumstances, under that particular wording, that phrasing, you give both the function and the associated domain with that. Whereas if they say rule, you just give the rule of the equation, which is why we then have to go and put in a bit more effort into getting the equivalent, the required domain for this. Okay, so what we have here, this is still the this is still the same thing that's been transformed by Q. So we're still constrained by our Q domain that we had from earlier. And so we're essentially, long story short, just going to be borrowing the theta value from earlier. You can imagine that, so we knew theta being pi over 3 made us tangent. Right, that was the maximum at which this would work out. And so basically from there backwards is going to be our effective domain for theta. So whether you put that in full function notation or you do something like this is up to you. I've excluded theta 0 because 0 as Q is excluded. So theta 0 would mean a horizontal line, but the only way you get that horizontal line is if Q is 0, right? So if you remember, Q was not allowed to be 0. If you chuck that in there, you would get a horizontal line. Cool, that's that. We're about to hit time, so I'll just sort of flow through this one. It's actually a fairly short solution, all things considered, especially considering it's 2 marks. Maximize the area of the triangle. That's fairly chill now, because we have an equation, it's just sine theta, it's defined from 0 to pi over 3. We've kind of already done all the effort of helping us out here by getting this domain. Because if I just said your function is sine theta, maximize it, you just shove pi over 2 as your theta value, because that'll give you sine equals 1. But because we're restricted between 0 and pi over 3, the new biggest value is going to be when you shove in pi over 3. That's pretty much all there is to that one. If you really wanted to, you could go through derivative equals 0 stuff. And you're forcing cos to be 0. It can't quite get 0 because again we've got a domain issue, and so the minimum possible cosine is going to occur at pi over 3. That's a bit weirder to go about. This is probably a bit more appropriate. Just imagining, cool. From 0 to pi over 3, the biggest possible sine value is going to be when the angle is tallest. And that's it. That's all those questions. So in order, that was a pass rate, starting at when we did the Q stuff, it was pass rate of 6%, 4%, 1%. That was the previous question. That was this one, 1%. Back to 4%. So ridiculous stuff. You're not fully expected to get these right. The fact that we were getting, a decent amount of understanding, at least, like this question, is a testament to skill. But okay. If there's anything left to clarify from that, feel free to let me know. Otherwise, I'll let you enjoy the rest of your day.
Thank you.
No worries.
See ya.